9 o'clock, or do you know the time? Okay, welcome to the talk on IPSEC Opportunistic Encryption using DNSSEC. The talk's basically in two parts. One part is the DNSSEC part, where I'll do an overview of how DNSSEC works. The second part is about opportunistic encryption, which is a way for IPSEC to actually use the DNSSEC information to build lots of tunnels. Here we go. If anybody has questions, feel free to ask them right away. I think I'll go through the slides pretty quickly because I don't have that much time. So feel free to just get my attention and ask a question. So the first question becomes, why do we need DNSSEC? We've been waiting for a long time to actually get a secure version of DNS. The DNS is easily spoofed. There's no check on who's sending you the answer. It's pretty guessable. You'll know the problems. I'll talk a bit about the theory, talk a bit about how to use bind with DNSSEC. I'll show the example of how to securely register domains in the .nl tree, how to make them secure. It seems that .nl so far is the people who are furthest along with deploying DNSSEC. And I'll talk about deploying DNSSEC on a bit of a large scale, which is relatively speaking, but it's the ISP that I work for that actually has deployed it for all its customers. And the second part goes about opportunistic encryption, what it is, why we want it, how to protect it, install it, testing it. And the last thing might be very interesting for some people. The last bit is about WaveSec. We'll be running a few WaveSec servers at the conference. I'll talk about WaveSec later, but basically it's using IPSEC without prior arrangements to secure your 802.11 connection. The boxes haven't been set up yet. I'll do that after my talk. But if you want to know about how to actually deploy it and use it at the conference, just catch me somewhere and I'll be happy to help you. So one of the non-technical problems of DNS is actually that there's so many people involved who actually have some sort of control over your domain. I've just listed a few that I could think of for the domain freeswan.nl, which if you see that of course there's the root registry, various sign and various organizations from the root. We've got the more or less IETF run root name servers spread out all over the planet, doing their thing, which everybody's using it. Though not as critical as some people might see, because if they're getting lots of DDoS attacks, but usually people don't notice this. But in theory, if these data on these servers change, your domain could vanish. For the freeswan.nl domain, we continue to the country TLD servers. For NL, we get to write the regional internet registry in Europe. We also control, for instance, the reverse DNS tree for IP addresses. For the forward, we get to the Stichting Domeinregistratie Nederland, which is the Dutch registry. And then we get to my ISP, who also controls some of the reverse. And in between, we've got all the BGP routing problems and people who can actually just steal your traffic that way. Hopefully there are some other people addressing this issue. I know there's some working groups starting on secure versions of BGP, but hopefully it will take quicker than the DNSSEC one. So there are quite a few organizations actually involved in how to get to your domain. So how do we secure this? How do we get rid of 22 organizations out of this tree? Because we are the one that are running the domain, and we just want to say what data's in it. We don't want anybody else to change it. Well, this is a somewhat a quick view I did from the resolver point of view. You can see that if we want to know where www.freeswan.nl is, you can see that, well, first the answer is that IP address, but then if you closely look at where this question is being asked, again, it's all over the planet. We first go to usually our root file, get our root name servers, get an IP, ask for dot, continue on, get some glue, continue to find out where the name servers for .nl is, get some glue and name servers there, get to the ISP of freeze1, which is xtdnet.nl, continue on, and then finally in the end we get like an authoritative answer, which basically anybody can claim they're authoritative. It's not, we have no proof whatsoever. So that there's a lot of questions, a lot of places where people can interfere, and this is a problem of DNS. Well, so basically there are two types of vulnerabilities in DNS. It's the integrity of data and the authenticity of data. The first is basically like is the data that's being sent by the party who was supposed to answer changed before I received it. There's many ways where that can happen. I've listed a few of them. Last year there were some people at Black Hat that demonstrated some of this as well. There's of course the whole DHCP path. Before you get an IP number, who are you talking to? You have no clue where you are. How can you trust that the IP that you get won't be routed through monitoring stations, etc. There's another IETF working group working on securing the DHCP. They're also going to use DNSSEC to secure the DHCP, which is, I think, very interesting. You've got the client resolver problem, and no matter how secure your resolver is, and if your resolver is fully aware of all the DNS security and cryptography, if your resolver is half a planet away, you still have a problem of having that answer sent to you. The answer to that we'll come to later is basically you have to be your own resolver. Then there's the name server to name server propagation of information, various networking. So there's quite some places where things can go wrong, so I have to go step by step through the entire chain to get there. So what is DNSSEC? In short, it's protected DNS with a digital signature, and then verifying that signature that it's the correct party and it's correctly signed. Again, we need to secure the local area and the DHCP stuff. It's best to run the resolver on your own client. To secure communication between name servers themselves, we get the zone transfers, and we get dynamic updates, which are becoming more and more common to deploy for various reasons. Those need to be protected as well. And then, of course, we got the integrity if the server is hacked, if the cache is poisoned. That also needs to be secured somehow by these digital signatures. So we saw that the first attempt to do something about this was TSIG, which was basically mostly meant for two name servers to exchange the zone file, the master and the slave name server. And it was just like, well, let's do some crypto stuff, and let's just use a pre-shared key, and it will be secure, it will be encrypted. It's not very much in use for various reasons. First of all, of course, if you secure the data within your zone, if your if your zone file has been protected and every entry in it has been secured by a digital signature, transferring that data can be done in the clear without any checks, because you would find out if somebody messed with the data. So for communication between master and slave name server, you could do it in the open as long as you're doing it for secure zones only. Usually people set up also IPSEC tunnels between their name servers, or use SCP to copy the zone files, or use whatever secure database replication to actually get the data across. So though there are many people who just use the plain text zone transfers, I think the really bigger ISPs actually do protect this already without any DNSSEC going on. The second one is more interesting. It's the 6.0 that basically uses a public key cryptography. So we can just do more individual things. I can update my single record in the reverse tree without having access to the entire reverse tree, or without having a pre-shared secret with lots of people. 6.0 is definitely going to come and be deployed, especially on the leaves, on the end users, for dynamic updates. So this is the essence of the DNSSEC. There are 4 new record types that we put in the DNS and just distribute like regular records. First you have the key record. That's actually the public key used. The private key obviously does not go into the DNS. We keep it very securely on a signing machine. We've got the SIG record, which is the actual content of the signature created by the key. We've got the next record. I'll come back to that later, but it's a way to actually say that the data you were looking for was not here. And after long controversy on how to build a chain of trust, IETF has finally decided to adopt the DS record. I'll also get back to that. And there's a new flag in the resolver library that ships with bind as well. It's the authenticated data flag, which basically says this data was cryptographically secure. It was a proper signature. Though of course the flag itself is not protected by anything else, so people can just set the bit. So it's not used for actually trust, it's more used for debugging and seeing that you actually got things through secure resolver. So the key record looks like this. You got the name or the label, the TTL, IN key, and we've got some flags, protocols, algorithm, key material. Unfortunately, this slide is slightly out of date since December when IETF decided to change some things again. But the basic syntax hasn't changed. We've first got the flags, which has authentication or confidentiality. We've got the protocol, which is actually the change. The protocol is now only allowed to be DNSSEC. For people at IETF who feared that having too many records in the apex of a zone would actually load the DNS too much and you'd get too many queries with data that you do not want. So they're very afraid of these subqueries. This is one DNS query for a key record. But if you then have multiple applications like IPSEC or DNSSEC or SSH or other applications using this, people were afraid that you would ask like 15, 20 application key records before you find out what it was. So they decided on splitting the key record into various application key records with different typings and to separate this. So basically, if you follow very strict IETF rules, the key record can only be used for DNSSEC itself. It cannot be used for any other application. Then there's the various algorithms you can use. The most common right now is RSA SHA-1. Then we get the signature record. You can see an example here. There are 2 NS records, and then there's the signature over that NS record. First, you can see the type covered. So the signature actually says this is a signature for the NS records. The algorithms, again, the algorithms like on the previous slide. You can see the amount of labels covered in the signature. It says 2 because there are 2 NS records. To save some space, matching types are always protected by 1 signature. So if you got 15A records, you have 1 signature for that name. If you have 10 MX records, you've got 1 signature for all the MX records. Some things to notice here is that to prevent replay attacks, it's important that we cannot just trust on the TTL anymore. The TTL in the packet says when the packet has expired and should not be used and should be no longer stored in caches and fetched from the original source again. Of course, this allows for replay attacks. If I have a signed DNS packet and I store it for a year and then for whatever reason the original information changed and I can then use it again to point to a different location, the signature is correct because it was made by the original signer. So that's why there's actually now a SIG expiration and a SIG inception date embedded in the signature. So that allows us to prevent these games from happening. The signer name, the key material. This is an example of how it looks like. In further slides, I often abbreviate the crypto to make the slides more readable. So now the next record. There's another controversy within the IETF actually. what if a certain record doesn't exist, like we're asking for www.freeswan.org, and let's say that the record doesn't exist. We need to securely say that that record doesn't exist, but we're not signing on the spot. We sign zones and then we publish the zone. So we can't give a signed answer for every weird question that we get that we don't expect. So we need some standard way of saying what you asked is not here, and then sign that answer beforehand. So the idea with the next record now is that we actually point to the alphabetical next label. So if you're asking for gamma.freeswan.nl on a DNSSEC aware name server, if you're asking for data.freeswan.nl, you will get this record back that I've displayed, which says alpha freeswan.nl is one record. The next record is actually gamma.freeswan.nl. And this record, again, is signed for the SIG record with a signature. So that means that you now know securely that there's no beta or any records between alpha and gamma in the name. So no matter what people ask and come up with the host names to ask your server, you have the answer ready. So this is signed. People know that the answer is there's nothing in between. One problem with this is for domain registries, the big domain, the top level domains, because this means if I'm just asking for AAAAA.com, I will get the record that says, abc.com is the next domain. Then if I just ask for ABCD or ABC, I'll get the next record. Basically, I can walk the entire DNS tree of large top level domains and get the entire domain listing, which people don't like. Even though the information is public, somehow the collection of information is proprietary and people don't like this to leak out to prevent spammers from getting lots of domain names. This is the key limitation of the RFC that happened in December for people who are afraid that there are too many key records. I'll be talking about opportunistic encryption in the second half of this presentation, where we'll see that this is really unfortunate for us because the Freeswan people were actually using the key record to store IPSEC host keys. We also did it in TXT records. We had a choice. We preferred key records, but IETF decided that it has to be a new record type. So the Freeswan project is falling back to TXT because new records that still need to be agreed by the IETF will just not be ready to use and massively deployed yet. So it's a very unfortunate RFC. So a small example, I hope it's readable. This is the example for a stripped down version of a standard zone. I took freeswan.nl. You can see there's two NS records, there's an A record, and there's an MX record, and this is the standard SOA record. After signing it, the zone looks fairly unreadable, especially if you haven't seen all the key material, which I mostly cut out. You've got a SIG record over the SOA, two NS records, a SIG record over the NS records, an MX record, a SIG over the MX record. You've got two key records, not one. I'll come back to that later. And there's actually two signatures made over the two key records. Basically, this zone has two key records and they're both signing things. And then we see the next record pointing to www.freeswan.nl, which is signed, and then we get to the next record. And the whole thing happens again, and we see at the end, the next record of the final record actually points back to the apex of the zone. So it loops around. So this is the essence of how one zone is secured. Anybody have a question on? Is this somewhat clear? Okay. So we go on. Now one organization has their zone secure, but now you have to securely end up at that organization. So we have to build a chain of trust from the root all the way down to this secure zone. So we have a few problems. The parent of a zone does not have any, or should not have any key record. So the parent cannot sign anything saying, well, this child is the child zone is over there, and you can trust me on this. So So the parent has no key to actually sign it. The parent also from organizational point of view should not say anything about the child zone. Just like in regular DNS, it's passed along as a hint and sometimes with some added glue. It's basically saying, well, we believe that the child is there, but you better ask the child again yourself if you found something there. That's obviously not good enough for DNSSEC. So the parent needs to still give this hint, say, well, the child is probably at that location, but then also needs to somehow securely say, well, if you find the child, then this is it. This is the real child. So for that, there's the DS record. The DS record is basically a hash of the key of the child zone put into the parent zone. So what this means is that if you have a DNSSEC secure zone, you have to somehow communicate the public key of that zone to your parent, who will then run a hash over it, put it in its zone file, and then sign it. We can see here, this is the parent for freeswan.nl. We can see that there's ns.xdn.nl and ns1.xdn.nl, two name servers, which are not signed because the parent does not sign it. It's just a hint where the name servers are. It's not any way authoritative or cryptographically secure. And then we just see the DS record for the freeswan.nl zone, which is signed by the parent key. So this is signed by the .nl key, not by the freeswan.nl key. Then with the DS record in cached, the resolver goes to the name servers on the xdnet.nl domain, asks again for what's the key record for freeswan.nl, gets the key record, calculates the hash and see if they match. And if they match, then obviously it's been sent to the right place. If it doesn't match, then there's something wrong and it will give a surfail error. And of course this works up the chain as well. So for the .nl, they could give their key up, and the registry could actually, the root could actually sign for the .nl key. So basically we would only need one super secure key, and then everybody could live off in the entire hierarchy, and the world would be a happy place. Unfortunately, that's not the real world. First of all, not everybody is going to switch to DNSSEC from today to tomorrow, so there will be places where there's DNSSEC islands of secure zones and insecure zones. So the way to work around this, and the way to also prevent various institutions having to trust the root key and just build the trust from their own part down, is to have secure entry points. A secure entry point is basically your own key for a domain which you implicitly trust. You put it into your configuration, you say, I trust this key. For instance, if you want to actually use the DNSSEC extensions in .nl, you have to put the NL key into bind. The example here is bind because that's the only DNSSEC aware name server at this point. So you put this key in your name.conf, and now you're trusting everything that has been signed from NL downwards by this key. Of course, you can also do this for your own organization. You make one key for your organization, and then you can actually delegate subdomains to your other departments, which can then do their own signing. So one of the problems of keys in DNS and is of course that at some point things will go wrong. Small keys can be attacked by brute force. Large keys are strong, but we don't want to use that much CPU. Keys can get stolen. There can be flaws in the keys. People can find out new hacks. The signing machine can be stolen. Lots of things can happen. Basically, at some point, you will need to recycle your keys. Even if nothing happens, your key, you should at some point stop using the key and get a new key. So you need to have some out-of-bound communication between parent and child to say, well, my key changed. You need to update your DS record. There are various ways to do this. There's actually one automated way being proposed by the DNSX working group as well, where this is a somewhat automated process which might be used for organizations themselves who want to just believe the trust inside. But for instance, domain registries will definitely not use this because they're just too scared something goes wrong. They want their liability covered. So to fix this problem of limiting the interaction between parent and child is to use two keys. One very strong key, which is the key signing key, and one key that you recycle more often, which is the zone signing key. So the best current practices at this point is to use a 768-bit zone signing key and a 2048-bit key signing key, and sign and use the DS record on the key signing key. So, for instance, you keep the key signing key for a year. You only need to talk to your parent to create a new DS record once a year, and you can still cycle your zone key 12 times a year if you want to. So how this works is the key signing key actually signs the zone signing key, and because the zone signing key is then trusted by the DS, it is trusted to sign the data in that zone. So this is an example of the phases you go through when you actually have to recycle through these key rollovers. In a normal situation, you have the key signing key, which has been signed by of which the parent has a DS record hash that's signed. The child has the key signing key and the zone signing key, which I've called zone signing key 1 here. And then the key signing key actually signs the key signing key itself and the zone signing key, and the zone signing key signs the zone. And when you prepare to replace the zone signing key 1, ZSK 1, you first have to add the key into your DNS, and then wait a while, and sign it with the key signing key, and wait a while for things to propagate. Once they've propagated through the secondary name service, once the TTL of the old stuff has expired, you can then tell your parent, okay, we've switched keys. Sorry, not tell, you can just switch the keys because all the data is out there. You can just remove that key later on. So this is completely in your control. You don't need to contact the parent because the key signing key doesn't change. The key signing key rollover is somewhat more complex because you need to tell the parent to change the DS record. It looks a bit complex. You have to take care of the caching times, the TTLs, the signature times. But there are tools now that actually do this for you, so it's not that difficult to actually do. The problem, of course, is if your keys get stolen anyway, or if there's a problem. One of the things people have been talking about is to put a spare key in your zone, which is signed anyway, which is securely locked in a vault. As soon as your key signing key gets compromised, you just switch your DS. You immediately talk to your parent, change the DS to the second one, out of bound by a phone call. And then at least you've contained the disaster quite a bit. If you have to wait for signatures to expire and you have to wait for a day or something, then you're vulnerable for the entire day. So having a spare key signing key in your zone is actually a good idea. Nobody's done this so far, but it's definitely a good idea. Once you've been compromised, you also need to make sure that you contact everybody who has configured you as a trusted key, because they will keep trusting that key no matter what's in the DNS. If you've configured bind to trusted key, it will trust the key. And you need to contact your children because something is wrong with the parent. The delegation can just go elsewhere without ever getting to the children. So I thought you'd do this yourself. Unfortunately, there's still no bind release that actually does all of this. You need to use the snapshot. The latest snapshot is pretty dated already. It's from December. You configure it. You use the switch with OpenSSL. For Linux, at least, the threads are completely broken, so you have to disable the threads, which might be a problem if you're starting your name server on a busy machine. Once it's reloading all the zones, it won't be able to do any queries. Some other tools. Do not use host awareness lookup. They're really old tools. You shouldn't use them. If you really like the layout of the host command or DNSSEC command, you can use dig plus multiline. For DNSSEC queries, you can use the dig plus DNSSEC. one thing to do note is that in the old bind 8 series, if you would actually let the signatures expire, it would mean that bind 8 would know like, hey, this record is invalid, even though it's properly signed, the time has gone by, this record is no longer in use, let's just remove it from the zone file. So the problem here is that if you actually just experiment with this stuff and you put it in and you run it on a bind 8 name server, and you, after a month, you forget about this, your zone will be gone. So either use bind 9 or just make sure that your data hasn't expired and it's actually continuing your experiment. So I'll quickly go through this. These are just the commands to use it manually. DNSSEC keygen with the proper parameters. You'll get two files, the k31nl file and the key ID and the algorithm. You get a private file and a key file. The key file you add into your DNS. The private file you keep very private. So, and then you use the DNSSEC sign zone to actually sign the whole zone. Of course, before signing, you have to increase the serial number because you cannot do that after you sign a zone. And then you upload it to your master name server and reload the proper zone file. And then you can test it with the big line that's displayed below. It's very good practice to not have the keys to sign the private keys on the name server itself. If the name server gets compromised, which you all know bind has a bad reputation for, then they have your secret keys, they can publish whatever you want. Use a separate signing machine and upload only the signed data, so that even if your name server is completely hacked to pieces, the only thing it can do is either send out data that's not being verified or send data that you actually wanted it to send. So they can still DOS your name server from the planet, but they cannot have fake records in there. This is just an example on how the NL experiment works. You select the key, you tell it what domain you want to secure. You select the key that you want to be used for the DS flag, and you get a record. And if you want to do a key rollover with the parent, they give you a random record, which you can see displayed in the green line. You have to sign it with your key, and then they know that you have the old private key, and you actually qualified to authorize the key rollover. This is what the big output looks like. Most important thing there is that you can see that there's an AD flag set. The AD flag means that it's cryptographically secure. The two name servers that you see are the name servers that you can use to do secure resolving testing for yourself. VeriSign is still using some old stuff. I'll skip it. They need to update their stuff to use the DS record. They're using some older stuff. I'll just skip through this quickly. If you want to do somewhat more massive deployment, like not sign every record yourself, there are Perl scripts written by Olaf Koopman from RIPE. And you can see some of the commands below. You can just type in like main key rollover, freeze one and no, zone signing, yes, and then it will just roll over in the first phase. You wait a day and then you do this again, and then it will do the rollover of the second phase. It's all very much automated. We use this to maintain over 150 domains. .nl domains in this case. The tools are there to actually make it work, so go experiment with them, go use it. I'll just briefly skip through this. You need to make sure that your signing machine is very secure and it's not your name server. So now, why DNSSEC? Why am I actually using and pushing DNSSEC? It's because I'm actually pushing something called IPSEC Opportunistic Encryption. That's one of the applications that's actually using it. Some other application, OpenSSH, has an old patch out there that actually uses can work with the known host file. And if the key is in the DNS, it just knows the key and doesn't prompt you for, do you really want to connect to this host? The ISC, the H client, has some secure dynamic stuff in there. And there's some next rock software, the abuse I talked about earlier. References you can just look up in the book. So let's go to opportunistic encryption. Basically, IPSEC is the tool or the protocol to use to secure your IP to IP communication. However, the classic IPSEC deployment requires that you talk to the other person, you agree on the parameters used, you either agree on a pre-shared secret, or you have to know which key the other side, which public key the other side uses before you can actually set up a connection. That's fine if you want to do VPNs. You can configure this once and forget about it. However, it's not going to completely encrypt the entire internet, which is actually the goal of opportunistic encryption. So we'll talk about that quickly, how you can use OE to protect the net, how you can install and configure it. And we'll get to the WaveSec part where you encrypt the wireless. So IPSEC in a nutshell, the first part, make sure that there's only a one-on-one communication with the Diffie Hellman key exchange. Even though you're not sure who you're talking to, you at least know you're talking to one person and there's no eavesdropper in the middle. And part two, then basically you exchange identities and say, well, I'm this person, oh, you're that person, okay, well, I know who you are, let's now set up crypto. So opportunistic encryption wants to do this without prior arrangement, and of course, as you might have guessed, we are going to put the keys into the DNS, because of course we've secured the DNS with DNSSEC. So this is a TXT record that is actually the record of my machine at home. The TXT record for 17.1571 and 10.193 in other ALPA says that if you want to talk to me securely using IPSEC, then talk to this IP number, which is itself, and use this public key. Now, since the XDNet NL zone has been signed with DNSSEC, nobody can fake the key for the IPSEC tunnel. So now anybody can just query this record, get my key, and then set a connection up to me. Because the previous RFC 3445 problems where the IETF decided that keys should only be used by DNSSEC and not IPSEC, we had to move stuff into TXT records, but you'll see that most of it also is supported with the old key records. So somewhere in this IPSEC negotiation, the parties send each other an ID, and this is where we hook into with our opportunistic encryption. We say, well, if the ID starts with an @ symbol, we just assume that everything after the @ symbol is a fully qualified domain name, and we just query the key from the DNS. So for instance, if the ID is @bio XDNetNL, then we actually do not use the IP address for information on how to set up a tunnel, but you actually query for the record, for the TXT record of via XDNetNL. So this is basically how two machines who've never talked to each other before can use DNSSEC to talk to each other. Of course, at least one side needs to have this TXT record in the reverse. If both sides have it, then it's not good enough. Sorry, if none of it have it, it's not good enough. One of them has to have it in the reverse. Since not all people control their own reverse yet, this is not always an option. But most of the servers actually do control their reverse. So the servers usually have this record, and the client can actually get away with telling its ID in the IKE exchange for the IPSEC tunnel, which is also secured by the IPSEC protocol, so they can actually then tell them who they are. So the downside of OE is that it takes a few DNSSEC queries to actually set up your connection. It can take time, it can be annoying. People want the website to appear instantly. So for busy web servers, there's a way to do this passively. Like you don't try to set up a connection for every package you get. Like if it's a new IP, you don't immediately go try and set up an opportunistic IPSEC tunnel. You just wait until the other side initiates to you. This is running on our web servers fine. There are not too many people yet using it, so there's no performance issue whatsoever. People who don't support opportunistic encryption don't see any latency. That's the passive OE part. So after basically when we set out to do host-to-host encryption with our prior arrangement, we actually also ran into the problem of the wireless being very insecure. So at some point we came up like, well, how about we do OE in a somewhat different way and make sure that we can actually just talk to a secure server and just encrypt all the local wireless traffic. So that's what we call WaveSec. How it works is any OE-capable machine, when it's sending out a DHCP request, actually also sends out its public key and says, no, I have this public key, I would really like to do, I would really like to build an IPSEC tunnel. Then if there's a WaveSec server, it will actually respond with a DHCP answer that says, oh, okay, well, if you use this IP number and this key, then you can set up your tunnel. So that's what we have here in the network. We're still setting it up. It should work in a few hours if you want to try it. It works nicely next to the standard DHCP server because if you do not send your own key in the initial request, our DHCP server will not answer, and the regular black hat DHCP server will actually just give you an IP address. There are some issues with it. There's one man-in-the-middle attack possible where somebody else can say, oh, I'm the WaveSec server, you can encrypt to me. Which is a problem in DHCP, that DHCP is not secure. People showed this last year here. But they're working on securing DHCP with DNSSEC keys. Does everybody get the OE concept? The concept of having two hosts who've never talked before, use the DNS, get keys, get a connection running. Okay, a typical setup at home where people have ADSL, their own subnet with wireless. You can use WaveSec to secure your home. You can also use OE on your router box to actually encrypt everything over the network on the internet. So your typical ADSL setup with one IP, no control of the reverse. You run NAT. If you run it on the internal interface, most people run it on the external interface because they think it's easier. If you run it on the internal interface, then and you make sure that you've rewritten your packets with your public IP address before using IPSEC, you can actually protect them with IPSEC. Because once you've used IPSEC, you cannot change the address anymore, because that would just invalidate the packet. That's the whole point. IPSEC is meant so that you cannot tamper with the packet anymore. Most people also on ADSL at home or cable do not control their reverse, so they would use the initiate only opportunistic encryption mode, which means that once they look up a TXT record and know that the other end can do OE, they will actually send their own ID in the IPSEC negotiation, and the other side can then pull it from DNS. One odd thing here is that the first inbound packet might actually be sent in the clear if the other side initiates first. If some remote service talking to your ADSL router at home, the first packet will be in the clear, then the whole encryption cycle will be started. IPSEC in the Linux world has there's been quite some things going on in the last 2-3 months. Basically, the Freeswarm project, which was the IPSEC stack for Linux, had a policy to say that American citizens could not submit any code because that would be the US government would then have a say about whether or not they could use that code in the future. So Red Hat, for example, never included Freeswarm for that reason, and a while ago they started with their own implementation of IPSEC. We managed to talk to them to at least make sure that they put the opportunistic encryption hooks in there, and it's all beginning to look rather nice. It's still fairly buggy, but I think in 1 to 2 months we'll definitely have like all of this in the standard kernel ready to be really massively deployed. Because right now, even though Freeswarm ships with most Linux distributions, it's still such a majority of people using Red Hat that not too many people are using it. The requirements for if you want to do OE, so far, you can either use the kernel code from the Freeswarm project or the kernel code from the 2.5 or now 2.6 kernel. You need to have some sort of DNS support in your forward to put your keys for initiate only, or in the reverse if you want to actually put it on a server. And you shouldn't firewall some of the ports and protocols that you need. So how does Opportunistic actually work on the Linux level here? Basically, freeze-run predates NetFilter. It's pretty old. It's a couple of years old. So at that point, the only way to actually grab the packets you wanted was to actually use a special route and just use a virtual interface and fling it in. You can see that if you're not running OE and you do IP route list, you can actually see that there's, in this example, again, my machine at home is doing a standard 193.110.157 route and a default gateway. Once I enable OE, you can see these two routes marked in green, which is basically a really dirty hack of saying, I actually want to have the default route and I want to have more preference than a default route. So we cut this space in half by using a net mask of 1, and then grab the 2 halves of the entire net space and then tunnel that into the IPSEC device. And then if we, for some reason, cannot do OE to the other side, then it just defaults back to the default route. So if you look at the server side for OE, it keeps track of the connections of who actually has set up a tunnel and who hasn't. You can see that the trap means that, catch these packets and process them and see what we can do with them, which is, in this case, .17, again, is my machine at home. It's using OE, that's why it's trapping all these packets. The second line, you can see that this machine 131.174.124.204 actually was not able to do opportunistic encryption with us, so we decided to just pass the packets on in plain text. We still want to talk to it. The server next, we can see we have a tunnel. We have 193.110.157.10, which is actually the freeze-run web server, www.freezerun.org. Actually has a tunnel up. It supports opportunistic encryption, and the machine that's actually doing it for that server is 193.110.157.77. The hold is only when something definitely gone wrong. We should be able to do opportunistic encryption and protect the use crypto, but for some reason we can't. For instance, there's a firewall rule in the way packets are getting dropped, or the server actually doesn't support opportunistic encryption but does advertise it in a DNS. And tunnel means we have the tunnel up. Since freeze-run 2.x, the 2.0 series, and there's policies to make things easier, you can just edit these 5 files, put in network notation, say, well, I want all my company addresses to be private or trop. I don't want to fall back to the clear, and for the internet I want to do private or clear, and for some failed hosts I always want clear or on the block, and not talk to those IP addresses ever. So how do you actually install and configure opportunistic encryption? We've gone through quite some effort to make this like a non-configuration issue. It's, you should be able to get most RPMs for distributions, or Reddit RPMs we make as well, because they still don't ship it, or you can install from source. Let's go through it quickly. If you want NetT support, then you should download a fork which is called Super FreezeRun, which is about to be merged back into the regular FreezeRun tree, but it's still separate for now. Make sure you have GNP. That's a problem we often see when people try to set up the opportunistic encryption. They're missing some header files. You can just issue make all go in the FreezeRun tree, which will make all the IPSEC modules you need, which include the opportunistic encryption support. And you install them. If you want to have NetT support, NetT is net traversal. If you're behind net, there's still some IPSEC things you can do to break through it. Unfortunately, opportunistic encryption doesn't work through NetT yet, so for opportunistic encryption, you won't need it, but if you want to use it for other things as well, building tunnels, tunneling more IP addresses into your ADSL home, you can definitely use NetT. 2.5 is pretty experimental yet. Do not use the supervision tree, doesn't support OE hooks yet. Just make programs and make install. generate your key using the IPSEC new host key command. You can have the text records that you need to put into your DNS generated with these commands, --txt, and the IP number of the opportunistic encryption gateway or the machine that's doing the gateway, or your own IP if you're doing it yourself. You just can cut and paste these records into your zone file. Hopefully sign it with DNSSEC. And continue. This is how it looked to me, the 1.9 version of Freeform, which is still ships in most of the distributions. You have to enable this connection called me to anyone, which basically says with the magic keyword percentage opportunistic, try to do opportunistic stuff. This is the only configuration you need to do to enable opportunistic encryption. And if you actually do not control your reverse, if you cannot put a DNS record in there, and you only have the key records in your forward zone, then you need to enable the last line that says left ID is, so that we can tell the other side that that's where you fetch the DNS record. For the 2 series, we enable OE per default. You can disable it if you want, but in principle, it will try to find out continuously if the keys are available to use, and even if you don't put the key in there, as soon as you put the key in there, it will find out and just enable this connection and try to do opportunistic encryption. Configuring WaveSec is a bit more difficult. This is basically the configuration. You need a patch. This is basically the configuration to make sure that you don't interfere with the existing DHCP server in the network, and that you actually do a dynamic update to put the key in. There's some more links where you can see how you actually configure the server side. If you're interested in setting up your own WaveSec server, just find me in the corridors and I'll gladly help you. You need to have still a lot of these connections, unfortunately, to do manually to get all the encryption working. I'll skip through most of that. One important thing for the WaveSec is that you have a sort of bootstrapping problem. If you do not allow DHCP or DNS packets to flow first, then you can never actually set up, you actually not get your IP number and do your DNS verification of the key records. So the easiest way now is to just use this script to actually just make holes and just allow this anyway. This one also allows ICMP so that you can actually check that you actually have an internet connection. It's just that your WaveSec is not working for some reason. You don't actually need the Red Hat patch anymore. If you want to get the DH client configuration, there are 2 popular DHCP clients. One is the ISC DHCPD client, which is DH client, and you've got the DHCP CD, which Red Hat is still using. DHCP CD does not support any of the WaveSec stuff. So I recommend using the DH client, and actually Red Hat itself is also switching. You can see that on Red Hat 9 if you have DH client installed, and actually uses that in preference to the older stuff. It's actually also possible to use WaveSec, on FreeBSD or OpenBSD or anything that resembles Kami. One problem for OS X is that it's using a different DHCP client, which does not support the stuff we need, but we're talking to them and see if they can add the functionality for it. If you have a FreeBSD box and you want to try this out, also just find them in a holder. The problem with Windows machines, of course, the best thing is to have opportunistic encryption working for Windows machines, because that's still the biggest amount of machines out there. The problem is that they want to use their own things, of course. So you either have to put keys in certificates, or you have to put keys in LDAP, and then retrieve the keys there and then set up the connection. There are some tools written to glue everything together, but at this point there's nothing working for opportunistic encryption on the Microsoft machines yet. It does work if you use some of the other clients like SSH Sentinel, but not many people are working on that anymore since Microsoft released their own IPSEC native clients. If you want to test OE, the easiest thing is to just use IPSEC verify first to see if all your things are working. Most common problems we check if you actually have the IPSEC kernel support, check if the daemon runs. We do the DNS checks. In this case, you can see that the DNS check for both h.exe and now failed. So it cannot do opportunistic encryption in this case. It also checks if there's more than one interface that's actually forwarding packets. And it checks if once you're doing IPSEC that you're not trying to kill your packets by rewriting them afterwards. If you go to untitled.xdnet.nl, that's actually the first public test server out there that actually supports all the DNSSEC extensions as well. So even though for now it's just informational, if you actually connect to it, you will know that it will tell you either whether you're connected using simple IP or whether using IPSEC or whether using opportunistic encryption and whether using opportunistic encryption with identities protected by DNSSEC. This is the output of one session where it's actually protected by DNSSEC. You can see the identity below and the key used and retrieved from DNSSEC. Some other test sites you can use that all support opportunistic encryption. Some known problems with OE. Once you start OE, once you want to verify keys in the DNS, again you have the problem of someone will initiate, or you will want to initiate a connection to somebody else. For that you will need a DNS answer. That will initiate a new connection to your DNS server, which of course triggers another opportunistic encryption session. And they will all fail until at some point you get these pass routes and said, well, the DNS, we cannot reach the DNS servers. We'll just use the flow, let these packets flow in the plane. So the first 10-15 seconds you should not rely on opportunistic encryption. It just needs to somewhat slowly start up. And you can limit it somewhat if you use the IPSEC policy groups that I showed before and put your name service in the always clear section. Then again, you might not want that because you actually want your DNS traffic to be encrypted as well. There's some issue with PCMCA cards that we need to work on. If it starts without a default route, if there's no IPSEC connection, if there's no network interface, it doesn't really handle it well. Or if it disappears or if your IP number changes, it needs to restart things. We're working on it, but there's some silly bugs there. One of the really bad things with WaveSec right now, really strange bug, is that if you on some laptops, like for instance on my laptop, but I'm not the only one, if you insert the card and the kernel actually generates a kernel event that actually starts the hot plug subsystem, it actually starts the DH client, and for some reason, at some point your environment gets corrupted and it just doesn't work. If I then just wait and run DH client manually, it works. This is some bug in pclose, which if somebody knows more about this, I'm happy to demonstrate it if they know how to fix it. 2.0 cannot talk to 2.01, that's because of the key issue before. Sometimes if you're tunneling deeply, tunnels within tunnels within tunnels, which some of the cheaper ISPs do a lot, adding your own IPSEC tunnel can actually just trigger MTU problems. For instance, Slashdot is known to just kill packets that are too small. So if you're getting, you can try and play with the MTU once things are failing. 1450 seems to work fine if you run into this problem. There's lots of debugging standard, like FreeScan does a really good job of logging a message per event. So really check your log files, it will say what's wrong. Run the IPSEC file, disable your firewall rules to see if you're actually not just killing the packets yourself. There's a tool written called IPSEC, which you can actually test to see if your ISP filters out some of the IPSEC ports. And if that all fails, then you can use the command IPSEC bar, which will basically dump the entire state except your private keys into a file, which can get fairly big. Just post on the website and then ask on the mailing list and we can help you with it. People often make the mistake of enabling Clips debug and Pluto debug, which is actually only meant for developers. Once you do that, the IPSEC bar for output becomes several megabytes and we just cannot read through all of it. So do not enable it unless you are a FreeSwan developer. So if you want to try out Opportunistic Encryption, just grab me or try to download it and grab stuff. One problem at this conference right now is that, of course, we're behind NAT. So talk to me if you want to try and use some real IP. We're going to set up an IPSEC tunnel to turn some real IP into the conference and then use that for the WaveSec. People want to try out Opportunistic Encryption. And then hopefully in the near future everything will be completely encrypted end to end and we can all follow Phil Zimmerman in his privacy and human rights issues. I can demo some of the things, but I'm somewhat limited because of my NAT connection. So are there any questions people have? Yeah, the FreeSwan has kernel code which is called Clips, which you can use. The Red Hat people are making the Linux 2.6 IP stack, the AF key stuff. We're working with them to make sure it works. The hooks are in there, the patches are in there to use the BitKeeper tree from Dave Miller, and you should have the latest patches to actually use it. You should also get the latest development version of FreeSwan, like 2.02 pre-0 at least, and then it should work. There's still some issues to resolve, there's still bugs in the kernel, but we're making this work with the new kernel IPSEC code. Sorry?
What is untappable running that produces this output relative to the Gopher port?
Basically, it's just running some test and debugging stuff that it will just output on the Gopher port. It's actually if you download FreeSwan, there's a testing directory which actually contains the stuff. It's using the bind DNSSEC resolver, the library resolver thing. So I think it's called LWQDNS. It comes with the bind snapshot, and it's actually using that for the DNSSEC part. Basically, if you want to use DNSSEC on the Opportunistic Encryption, you basically have to just run your own secure aware local resolver. So you have to run bind with DNSSEC stuff on your local machine. There's just no way around it, because otherwise everybody will have to recode all the DNSSEC routines to verify everything. And people are just not going to do that, and they're just going to say, run your own secure resolver and let that do it, and then we have one code base that does the security checks on the crypto, and not everybody has to write their own code and make new mistakes. Okay, thanks.